So let's briefly discuss the 4 laws of thermodynamics, and let's try to build a relationship between these 4 laws. And let's begin with the 0th law of thermodynamics. So let's see exactly what it states. If 2 systems are in thermal equilibrium with a 3rd system, then that implies those 2 systems must be in thermal equilibrium with one another. Now, before we look at the following case that confirms this law, let's define what thermal equilibrium is. Thermal equilibrium between any 2 systems simply means there is no energy flow between the systems as a result of a difference of temperature. So no heat takes place. And that's because those 2 systems, if they are in thermal equilibrium with one another, then their temperature must be equal. So let's suppose we have system 1, system 2, and system 3. Now the temperature of system 1 is T1, the temperature of system 2 is T2, and the temperature of system 3 is T3. Now the 0th law of thermodynamics states that if the temperature of system 1 is equal to the temperature of system 2 and the temperature of system 2 is equal to the temperature of system 3, if T1 is equal to T3 and T2 is equal to T3, then that implies that T1 must be equal to T2. If this wasn't true, then that means these systems would not be in thermal equilibrium with one another. So let's move on to the 1st law of thermodynamics. The 1st law of thermodynamics essentially gives us a way to quantify energy flow. In other words, it's a statement about the conservation of energy. So in any process, the change in internal energy of our closed system is equal to the energy that flows into our system as a result of heat, as a result of change in temperature, plus the work that is done on our system by the surroundings. And this law can be given by the following equation. So the change in internal energy of our closed system is equal to the Q, the heat flow into our system, plus the work that is done on our system by the surroundings. Now, if the heat flow was out of our system, this Q would be negative. And if the work done was by our system, this would be negative. The W would be negative. So once again, this law, the 1st law of thermodynamics, is a statement about the conservation of energy. Now, we know there exist processes in nature that obey this law of thermodynamics, yet do not actually take place. For example, we know energy never spontaneously flows from a lower temperature to a higher temperature. So this process doesn't spontaneously take place, even though it actually obeys, it satisfies the 1st law of thermodynamics. And that's because of the 2nd law of thermodynamics. So let's see exactly what this law states. The total energy or the total change in entropy of any type of system plus its surroundings will increase for any real process. And let's see exactly what that means by looking at this equation. So the total change in entropy is equal to the change in our entropy of the system plus the change in entropy of our surroundings. And this sum must always be greater than 0. In other words, if the change in entropy of our system is negative, if the entropy of our system decreases in any natural process, then that implies the entropy of the surroundings must increase by a greater amount, so that our sum is always greater than 0. So we see that entropy dictates whether or not a process or a reaction is spontaneous. So this essentially explains why certain processes that obey the 1st law of thermodynamics yet don't actually take place. And now let's move on to the third law of thermodynamics. So this law essentially states that absolute zero is impossible to reach. So it is impossible to reach absolute zero, 0 kelvins, in any number of finite processes. And this can be readily seen by examining the following equation. So recall that the Carnot engine is essentially an idealized version of a heat engine that uses a reversible cycle known as the Carnot cycle. So the efficiency of any engine that utilizes the Carnot cycle is equal to 1 minus TL divided by TH, where TL is the lower temperature of the object and TH is the higher temperature of the other object. So we see that if this value, if TL becomes 0, this fraction goes to 0 and our efficiency is equal to 1. But we know an engine with 100% efficiency, with an efficiency of 1, does not actually exist. And that means this numerator, this value, can never be 0. And so that implies that absolute 0 can never be actually attained.